In previous experiments, we've used the standard deviation in a multiple trial experiment as a total measure or a estimation of the total amount of uncertainty associated with the protocol. Let's consider now an experiment where we only do one single trial consisting of multiple measurements. We need to now figure out exactly how much error is associated with that measurement. What we can't simply do is add the error together. Because you can imagine if we have two numbers, x with its uncertainty and y with its uncertainty, taking these and adding them together, let's say, and just saying now we have x plus y plus or minus the uncertainty in x plus the uncertainty in y, this doesn't take into account one very important thing, which is that it's very possible for x to have been under and y to be over. And if that's the case, the uncertainty would be large. But what if x were over and y were under? Or what if they were both under, they were both over? We need a better measure of the total amount of uncertainty. And so for that, we're going to propagate uncertainty. So let's take an example. Let's say we have 1.55 plus or minus 0.03. And we'd like to add to it 1.21 plus or minus 0.02. So again, we'll call the total, t plus or minus the uncertainty in t. So getting the actual total is easy, 2.75. But the uncertainty in t is a little bit less straightforward. We're not going to simply add those two together. We're going to use the root sum of square method. So the root sum of square method says that for addition and subtraction, the square of the total uncertainty is just the sum of the square of the individual uncertainties. So this would be uncertainty in x squared plus the uncertainty in y squared. So that would be 0.03 squared plus 0.02 squared. So to get the total uncertainty, I would just take the square root of 0.03 squared plus 0.02 squared, and I get 0.036. So notice it's greater than the uncertainty of the largest uncertainty, but it's not as large as just adding the two uncertainties together. And this makes sense. And so we would say that we have 2.75 plus or minus 0.036, or 2.75 plus or minus 0.04. So that's good for addition and that's good for subtraction. When it comes to multiplication and division, this becomes a little bit more difficult. So let's take the same set of numbers, x, which is 1.54 plus or minus 0.03, and y, which is 1.21 plus or minus 0.02. And instead of adding them together now, let's divide them or multiply them. So let's take the product. So x times y in this case is 1.86. And the question is, what is the uncertainty in this value? Now, unlike in addition and subtraction, we're not going to say that the total, so let's call this t for total, we're not going to say that this is the sum of uncertainty in x squared plus the uncertainty in y squared. That's not going to be the case. We're going to have to use the percent relative uncertainties. So what we say is that the percent uncertainty in t squared is equal to the percent uncertainty in x squared plus the percent uncertainty in y squared. The reason for using the percent uncertainty here is a little beyond this course, but for those interested, take PChem Lab or take a course in partial differentiation, and it comes out very nicely. How do we get the percent uncertainty in something? So the percent uncertainty in t is just the uncertainty in t divided by the actual value t itself. So what's the percent uncertainty in x? Well, that's the uncertainty in x divided by x. So in this case, it's 0.03 divided by 1.54. So if we do that, we get that the percent uncertainty in t is equal to the square root of, in this case, 0.03 over 1.54 quantity squared plus 0.02 over 1.21 quantity squared, and we get that the percent uncertainty in 3 is equal to 2.555%. Well, that's very nice, but we'd like to actually get the uncertainty in the product. And if that's the case, we'll just multiply the percent uncertainty times the value itself and get that 2.555% of 1.86 is 0.0475. So we would report this as 1.86 plus or minus 0.0475, or 1.86 plus or minus 0.05. Okay, a couple more little nuances before we finish. What if we have, let's say, 3 times 2.2 plus or minus 0.1? Is this multiplication or is this addition? So any time we have an integer multiplying, or a whole number multiplying a real number, remember that this is actually addition and not multiplication. This is really 2.2 plus 2.2 plus 2.2, and so there the uncertainty, or the total uncertainty here, would be square root of 0.1 squared plus 0.1 squared plus 0.1 squared, 1 for each of the additions, which would give us 3 times 0.1 squared. And that 3 happens to be the same 3 over there. So that's a little bit of a shortcut there as well. Last and certainly not least, let's take the really complicated scenario, which is actually very likely. Let's say our experiment, we're trying to calculate z, and z is a plus b plus c minus d, entire quantity times f plus g, everything divided by h. Well, first we have to remember our order of operation rules. We're going to need to calculate the uncertainty in this guy, we'll call him x, and the uncertainty in this one, we'll call that y, and then we have to propagate it together. Now, before you start thinking that we have to do each of these separately, remember, we can propagate many additions and subtractions at the same time. So the uncertainty in x, and you can prove this to yourselves, is just the uncertainty in a squared plus the uncertainty in b squared plus the uncertainty in c squared plus the uncertainty in d squared, square root of the whole quantity. Similarly, the uncertainty in y, which is also addition subtraction, is just the uncertainty in f squared plus the uncertainty in g squared, square root of the quantity. And now, to get the total uncertainty, so the uncertainty in z, now this is now a product and quotient, so this is percent uncertainty, is equal to the square root of the percent uncertainty in x squared plus the percent uncertainty in y squared plus the percent uncertainty in h squared. And so there's no need to do each one of these separately. We can do all multiplications or division at the same time, or all addition subtraction at the same time. Only thing we can't do is mix additions and multiplications. Hope you found this useful, and this will save you guys a little bit of time in calculating your total uncertainty.